Hello and welcome to the wolfSSL live webinar, wolfSSL and Automotive HSMs, presented by wolfSSL engineer Bill. My name is Shizuka and I'll be moderating the webinar. All attendees will be in listen-only mode. If you have a question, please use the Q&A box. We will host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. I invite you to follow us on Twitter at wolfSSL as well as our other socials. Also, feel free to email us if you have any additional questions. And now I'd like to give a brief company overview before we move to the technical presentation. Today, wolfSSL secure over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of over 50 dedicated employees, most of which are engineers. This progress is of course supported by a strong partner network that we are proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO-170A support, HIPS certification, and HIPS ready offering, MQTT up to the V5 specification, SSHB2, TPM 2.0, a secure bootloader known as a wolfboot, as well as Java wrappers and JSSC support, and commercial support for Coral. All of those offerings are accompanied by through maintenance and support plans up to the 24/7 level. We also offer full service consulting, and now I would like to turn it over to Bill to talk about wolfSSL and Automotive HSMs.
All right, thank you, Shizuka. Again, my name is Bill Phipps. I'm an engineer with wolfSSL. I've been here just under a year, having spent my previous life, about 15 years in defense contracting, specifically on anti-tamper and cybersecurity solutions. So I kind of bring a aircraft and defense mindset to security, and lo and behold, automotive is now in the same boat as many of the defense contractors have been for quite a while, recognizing that internal security, specifically hardened with hardware, is really the way forward. So with that in mind, we wanted to take a look at what is currently going on in the HSM markets, specifically in the automotive area, how those technologies are the beginnings of solutions, and then we took a look at what we currently do in a software perspective and see how much of that can be reused or tailored or turned into part of an overall solution for an automotive space. So again, it's our opinions on where we see the HSM market, specifically for the auto, going to, and the point here is taking a look at where our wheelhouse is, which is an embedded software cryptography, and how we can help turn those into solutions. So I'm going to walk through some of the basics on what HSMs are, and we'll kind of dig into what we see as the overall model, and then how we, from a software perspective and a configuration and an engineering perspective, can try to help to move that ball forward in terms of an overall solution space. We'll finish up with a demo of some of our software running on an RX Tricore, which is a current HSM-based solution, microcontroller dedicated for the safety, secure, and automotive markets there. And we'll kind of walk through where we're going to end up. So right at the top, if anyone's not familiar with what an HSM hardware security module is, fundamentally from our perspective, an HSM is a programmable core that's really designed to make sure that we can get our cybersecurity, our cryptography, secured storage separate from the application space. And we need to do that because the cybersecurity aspect of it really needs to be scrutinized a lot tighter than the applications to make sure that we're doing crypto the right way. And having been in crypto, and wolfSSL has been in crypto for way too long, even simple mistakes can cause massive problems. And so we want to minimize that, segregate that physically into a separate core, and then allow those application cores, which are doing the infotainment or motor control or whatever ECU functions you've got to be able to call out and access a cryptography coprocessor, if you will, that can do that. But it's more than just the crypto that an HSM core is going to be responsible for. It's also going to be responsible to make sure that you've got a valid environment to be executing what the application cores need to be executing. And when I say valid, that means that the cores are executing the code we expect them to execute. It's been authenticated. We've measured it to ensure that it has not been tampered with. Likewise, there's data that the HSM core can hold onto for the application cores that can be protected physically. Things like tuning data or calibration data, or even feature release, features that you want to make sure that are not enabled on certain builds and are on other builds. The HSM core has those types of abilities that you would want to see to be able to protect application-based data that's critical. Private keys, unique keys that ensure that the vulnerability found in one box doesn't affect all boxes. So uniqueness is a big deal. And that's where the HSM is segregated out. It's typically a smaller core. Sometimes it's a different architecture. In the tri-core case, it is than the main application cores. But the idea here is it's a segregated area, offloaded, and you'll need a client library to poke requests and get responses from that. Additionally, the HSM core normally has access to additional lockdowns, hardware lockdowns that will, in essence, strap your chip into operating in a very specific way, one-time programmable, things like disabling test interfaces or JTAG or Nexus. Those are all features that the HSM core will normally have access to. And thankfully, we're seeing a lot of the same commonality between the different vendors and how they're segregating functionality out there. At the end of the day, though, the critical aspect of an HSM and the offerings that we're seeing today is that it's a toolbox. It is not a solution. These are the building blocks for which you can build your security solution on top of. And it's non-trivial. There is a lot of work to be done there. So let's keep moving on. So from one perspective, our experience with TPMs and other types of secure elements, we kind of saw the HSM almost in a scale or a gradient of what's possible. HSM being in the middle. The criteria I selected here was, I compared it against a separable trusted platform module, which is what we're used to in desktop environments. And then likewise to like a TrustZone or a virtualization solution, hypervisor-based solution, and kind of wanted to show where the HSM physically fits in that spectrum there. From a programmable perspective, the HSMs that we deal with are fully user programmable, as well as anything that's done in, say, a TrustZone or a hypervisor, whereas a TPM is not user programmable. It's a fixed device, and you're kind of stuck with that. From a coupling perspective, TPM is almost always outside of the chip. And so it's not tightly bound. It doesn't have shared memory access to be able to do work for you. So you're always constantly sending data over and getting it back. Now, that may be an advantage, meaning that exploitation of the main chip doesn't exploit your secrets. But in this case, from a tightly coupling perspective, it's different. Obviously, TrustZone operates in the same memory space, but you can limit those things out, or even virtualizations in the same boat. HSMs that we see in the market today do operate in a global address space that's shared with the application cores, or at least it's windowed into that same address space. From a hardware cryptography perspective, the TPM absolutely does standalone cryptography. What we've seen in the HSM market, most HSMs do hardware crypto. Some of them are very limited, so you have to very carefully pick and choose the HSM vendor that you're going with to make sure it's got the acceleration to do the features that you need to do the way you want them to do them, as opposed to having to implement everything in software. And again, the HSM cores tend to be slower, smaller, less feature, fewer features to have. So doing things in software is a penalty. Now, the fact that you're in a separate address space and in parallel with the other cores, you might be able to make up for it. From a pure TrustZone or virtualization, there's no hardware crypto that you're given. So that's one of the drawbacks of going with a shared address space solution like the TrustZone. From a physical protection perspective, absolutely TPMs are great. HSMs, they offer, a lot of them have tamper sensors that can identify if a chip is not complete or not intact. You've got separable areas of flash and programmability or non-volatile programmability stuff that is make sure that only the HSM can access that. And once the chip has been locked down, from a production perspective, you can't gain access to that except through the HSM. So those are some huge pluses, places to store private keys or other private material. I put TrustZone as a parcel from a physical protection because it does have features that can limit address space access, specifically DMAs coming in from unexpected locations. But that's nothing like the physical hardware protections, the barriers that are put into place for TPMs and HSMs. Non-volatile storage, obviously TPM has limited amount, HSMs the same amount. That's critical for the use case where we're trying to store secrets in a secure area that's separate. Not critical, but it is very handy to have that stuff completely separate from the application flash base. Obviously, TrustZone doesn't have any of that. From a tamper response, the TPM itself can self-protect if it detects it's in a bad spot. You can flip a switch and basically blow out any of the keys that you've got, but it can't protect the rest of the chip. HSMs, they tend to be integrated inside the chip, and so you're able to disable external interfaces if it detects a bad position, or brick it so that you can't get out of the boot loop any longer, and you're stuck in a failure analysis mode. Obviously, TrustZone as a pure software solution can't really do much in terms of a tamper response. So in terms of where we sit in the scale, I kind of see HSM kind of in the middle as definitely a lot of hardware, but it shares, because of the shared address space, it shares some benefits the same way a TrustZone or a virtualized solution would have. From our perspective, we see the requirements of an HSM is we've got to make sure that the HSM can support the secure boot of an ECU. It's got to be able to measure and authenticate the code to make sure it is intact, has not been changed. And when I say measure, I cryptographically measure is what I'm implying there, a SHA of some sort. Authenticate means digital signatures, making sure that the code is what we think it is from the day it was put together inside the factory or updated in system. And that's the other big deal, because cyber is a moving target. In-system update is going to be a critical feature. The HSM's got to be involved in that if you're going to do any cryptographic protection of those over-the-air updates. And so the HSM and its cryptographic features, as well as its non-volatile storage, is going to be critical in making sure that these updates over the air, which are mandatory, there's no way to avoid them, can be done in a controlled and a good fashion there. We also see that HSMs need to protect either calibration or configuration data. That's also important. So in addition to measuring code, there needs to be a way to ensure that the data is also intact and what the application is expected to be. Obviously needs to provide cryptographic operations, private public key, PKI, encryptions, hash, and signatures. These are all things HSMs are going to be required for. In terms of algorithm agility, obviously if you've got hardware offload for things like AES or SHA or any of the elliptic curve, those are great. But in terms of providing a software site to run things at, we're taking a look at post-quantum algorithms being placed into HSMs to give that next level of security inside some of these software-based HSMs. Again, ability to handle, debug, and test interfaces, turn those off, figure out how it's going to fit into the production lifecycle, and then still support failure analysis. The vendors have done a decent job of making sure that the HSM is a first-class citizen in terms of life cycle, but I can tell you the way you need to protect a chip to stop it from being hacked into conflicts with your ability to do failure analysis. So there's definitely a trade-off in terms of exactly what knobs you want to turn to protect the chip from tamper or from modification. And at the same time, you're just tying your hands in terms of what you can get from failure analysis. And obviously, from a real-time and safety critical requirements, HSM cannot get in the way. It's got to be able to support those things and do those things in a timely fashion, even though they typically are more limited processing powers there. So from a picture perspective, what we find is a reasonable, logical layout of HSM systems is you've got some separate HSM secured area. And this is could be physical, completely physical, could be a logical separation, but it's identified such that the HSM core itself has got a private chunk of RAM, a private chunk of non-volatile memory, access to crypto acceleration, and then access to some of those JTAG or debug controls, as well as sometimes even memory protection units that has access to turn off mappings or communications between the different cores. But the idea here is that there's definitely a fence around this area physically and logically to ensure that the HSM can operate completely on its own, but then be able to reach out and still see shared memory areas as well as shared flash areas from the non-secure side, which is on this side. Non-secure side, we're seeing multi-core, many of them usually in lockstep to maintain the safety criticality. And those cores themselves will have their own local RAM. In general, HSM cores and any accesses coming across the shared bus, generally HSM is allowed to poke at this memory, perform DMA operations. That's typical. There are ways of limiting that to ensure that a rogue HSM or a rogue application can't hurt each other, but those controls are typically in place. And we're seeing 2, 3, 4, 5, 6 cores, application cores. These are generally heavier CPUs, lots of cache, floating point units, the works. So from a model perspective, what we see, the way the HSM would integrate in there is from the HSM core side, it would perform a boot up of this core by itself, and that's generally a standard bootstrap type of code, perform whatever base configuration is necessary for the chip. And again, these cores may or may not be running at this point. Some configurations allow these to boot in parallel, others it's got to complete the HSM core boot before these cores are even released at a reset. And then after it finishes its boot up and its base configuration, it's simply going to listen for incoming requests that are sent through, again, generally shared memory interfaces with or with the interrupts and flag buffers to do that. So we see software delivery of a boot up sequence that can also set up these custom controls to clamp down the chip, as well as an HSM server, which is performing whatever requests are coming in from any of the application cores. On the application side, we see an HSM client library set that would allow an arbitrary user application to link in this library and then be able to issue those requests to the HSM and then be able to get the response back. So really, it's a pure client server solution. Whether the fact these are shared buffers to pass data or if they're simply passing pointers, that's something that's very specific in terms of what the platform can provide. But generally, it's a good mix of passing both data and requests, as well as using direct memory access capabilities of HSM cores to be able to grab the data or even direct DMA actions directly to the crypto acceleration unit. So logically, this is what I want you to have in mind as we're continuing through how an HSM ecosystem is going to be working. The good news is that Wolf has done a bunch of these things in the past. At least we see the puzzle pieces the way we've laid it out, and we say, hey, we've got some experience in doing things just like this, maybe from a library support perspective and maybe from a full-blown product support. So obviously, the ability for both the application cores and the HSM core to be able to execute software-based crypto, where the hardware maybe doesn't have those features that we're looking for. That's wolfCrypt and wolfSSL is our mainstay products and basis of a lot of our solutions. We've been doing that for multi-platforms for way too many years. And again, we have support for doing things like hardware offload. So we do feel like, hey, this is a good match for our base, skill set and how we normally will craft cryptography solutions. Wolfboot is a product that designed to do bare metal booting with access to NVM, where we can control and verify that the NVM has the data we're looking for. This falls right into line with one of the primary jobs of the HSM, which is to, obviously boot up the server and then verify that, any of the flash that we NVM application space and the data space is intact and safe to use. So wolfboot has a lot of the same types of mechanics, and it was pretty simple for us to go in there, grab what we wanted, and then move on. There might be some combination down the road, but for today, they're two separate product lines with a lot of overlap in there. Wolf TPM and our crypto callback features. So Wolf TPM is a product that allows us to be able to communicate with TPMs. To talk to a TPM, specifically when you're doing encrypted communications, you need to have your own crypto library and software as well. So Wolf TPM provides that interface as a standard, what's called a TIS, that allows you to talk to TPMs. We do see TPMs in a lot of other areas as a kind of a go-to solution for external hardware-based crypto. Haven't seen it yet in the automotive space, but based on how things move, it would not surprise me to see a combined solution. And in the military space, I'm very experienced. I've seen TPM solutions all over the place. So it does not surprise me it would not surprise me if I saw this also in the automotive space. Crypto callback is a feature inside wolfCrypt that allows us to redirect crypto calls to different types of backend engines. And this allows us to, without changing source code, necessarily the user space, to be able to route a call either to a hardware offload engine or to a software implementation if the hardware engine can't handle that type of stuff. But it allows us an isolation of the user software. PKCS11 is the crypto key interface. This is smart cards. This is normally how you would reach out to a secure element device. Wolf PKCS11 is a product that allows wolfCrypt to act as a PKCS provider. And in terms of external secure elements, this is the kind of the de facto standard of how to communicate with it. It would make sense for us to provide that type of interface instead of like an AutoSAR or a SHE interface to get into an HSM. So that's just some other experience there. And then lastly, the fact that we can handle non-NIST based crypto, either post-quantum, both pre and post, the approvals of those, ARIA, the SM cipher suites. There are going to be crypto operations that come out that are specific. She has a couple that are out there. So in this case, the point being is that we can handle alternate types of crypto depending on whatever the application is, and because it's an open source solution, we can support getting that shoved in there. So long and short of this slide is the fact that we see overlap in our existing history, our existing product space. And it seems like it's just time for us to see if we can put it all together and provide an intermediate solution that kind of goes there. From a design perspective, number one on the top of our list is to make sure that whatever we do here, we can open source and make sure that we can deliver source code to the customers for them to further customize. You should be able to see how we do this. You should be able to verify it, change it, and then you still get support on that stuff. So that was number one criteria for us. You'll find so a lot of these vendor libraries, you got to be under NDA to even talk to the chip. And I understand they're trying to protect their intellectual property of how they're protecting the chip and some of its features, but that makes it very difficult for potential customers to adequately compare these different solutions and then likewise not be stuck to a vendor lock-in. So just as a heads up, I won't be showing you any source code that's protected today, but just be aware that there are some criteria when you go to some of these vendors that you'll need to be able to sign NDAs to gain access to even some of the internals, how these things are supposed to be working there. One of the other major features that we want to do is to make sure that if the hardware crypto is missing something or could never do it, we wanted to make sure that we could provide those, step in software and implement those. Post-quantum is a great example of that. Some of the post-quantum verification algorithms are actually faster and smaller than even things like ECDSA. So it's one of these items you go, hey, this post-quantum stuff, it's stronger, it's smaller, it's faster. This should be exactly how we're doing that type of signature verification. At least have it on the table as an option. We wanted to make sure that their APIs didn't break. So as we're going between software and hardware offloads, again, from my perspective, that's the crypto callback. You simply invoke the call the way you've configured it, gets you it'll direct it to the right backend engine. Wanted to make sure we honored asynchronous op and real-time operations to make sure that we didn't get stuck in let's say a key generation loop for too long and all of a sudden we've missed our real time. So we've got roughly a 5 millisecond target for all of our executions to make sure they can pop out and say, hey, I'm still working, but we got to give the core some time to do other things. Apologize. We wanted to make sure that you could rip out features that you don't need. And this is something that's unique. If you take a look at some of the other firmware solutions that are from the vendors, you're going to get yourself an HSM firmware solution that is got everything that they can jam pack in there, even if you don't need it. And so this is, again, wasted space, wasted operations that you shouldn't have in your code if you don't need it. So one of the good things about the way we work at Wolf is being able to turn off features that you don't need and then verify that they don't exist any longer. That also reduces your cyber risk as well. Because we're open source, we wanted to make sure that if we put together a solution and you need to put something else on the HSM, it's not locked in. You can actually extend the HSM server code to add more features in there that are application specific. And this is exactly opposite of what we're seeing with some of the HSM offerings that are out there. They're thinking firmware, immutable. They're thinking it's coming from the vendor. The vendor knows best, but that's not necessarily the right case. So our goal here was to make sure that we could get to the point where you could place your own code in there in a reasonable fashion, verify it's doing the right thing without impacting the rest of the system, and then move on. And lastly, most of our systems, if you don't have hardware, you can't do much. So we almost always build a reasonably featured POSIX simulator. This also allows us to try out new mechanics even before we have hardware, or if the hardware is not available, or we can't get our hands on it yet. So that's kind of our design goals. From a functional design, again, we split it between two. HSM server, it's a full executable. It boots up, has NVM access. We're running wolfCrypt optimized for that core, that HSM core. And again, you'll see in the demo, we even run different versions of wolfCrypt depending on what we've got. Support the hardware crypto offload, implement security controls, make sure we're in a position to support a chain of trust. And by that, that means not only have we checked ourselves, we've checked the checker, and we've checked the guy who's going to be running after that. So those features are in essence built in to make sure that we can support, a chain of trust strictly through the cryptographic features that are within the HSM. And likewise on the client side, it's the same deal. Again, we port wolfCrypt so that even on the client side, not all crypto has to go through the HSM. Some crypto, like computing a SHA measurement, that's not protected. And as long as we do it right, we're good to go. So we do provide wolfCrypt on the client side as well. And then we offload to the HSM in cases that you don't want to do the job yourself, or you don't have the key material to pull that off. So fundamentally, this is kind of how the overall software of how we saw what wolfHSM can put together from a server executable perspective. We have a module that performs our basic core boot. It then executes the image manager, which generally would go and measure blocks of application code prior to releasing the cores, or in parallel to those cores actually booting, and then make sure that we've got a valid measurement that we've stored and we've provisioned ahead of time to see if what we expect we're booting up or going to be talking to is who we think it is. And then lastly, it just jumps into an overall loop that is looking for incoming communications that is coming from the application cores. This is all riding on top of an abstraction layer. The new modules that we're adding in for wolfHSM, it would be a full-blown NVM manager. I skipped off manager. We haven't worked that yet. This is, again, designed to ensure that access controls are being maintained. So either in product life cycles, certain pieces of NVM will have different amounts of writability or erasability. And then likewise, depending on which core is accessing and requesting, you may want to be able to apply access controls to those as well. It's not unheard of to not have full-blown access controls in the first rev of a crypto engine. I'll pick on ARM's PSA architecture, which is, again, that's the TrustZone stuff. They've never built access controls into the library, and they're at year 5 or something rather of deployment. So it's something that should be there in my opinion. But again, it's something on the side. It's kind of the icing on the cake, if you will. So Wolf server executable provides a full NVM solution to protect both its internal flash. And again, the flashes here are sometimes very limited. So you have to be very careful about how you do that. And there are going to be controls and how that flash operates that make it a challenge to use as general purpose non-volatile memory, as well as access to the main flash where the application cores would have access to. We provide a key manager that allows local keys, dynamic generation and storage of keys in RAM, as well as access to the hardware-based key stores. Most of the crypto engines have internal storage. It might be NVM or non-volatile, it may be volatile, but the key manager keeps track of which keys are where to make sure the operations can act the way they need to. We also provide a full wolfCrypt engine with software crypto. I put that in black because I've been using these in essence unmodified. Which is good. That means that, this is a good target for us. We didn't have to break a bunch of rules to make that fit in there. And then likewise, we add in a crypto callback for the hardware offload. Other platform or target specific items would be different IO and JTAG controls, how we do interrupts between the cores and the HSM itself, status data going back, and obviously the communication buffer. Again, for most HSMs, this is a shared memory space that both sides can access. And so in addition to properly organizing that, placing requests and responses in different areas, and then triggering interrupts, you can in essence come up with a pretty simple based solution. So from a server executable perspective, it's a handful of additional modules that are really tailored to the joint jobs of crypto, NVM management, and and then key management, which are a little distinct and different from what wolfCrypt natively does. From the client library perspective, we abstract all of the communication and all of the crypto and the routing through a client API, and then expose the NVM manager, but it's really the HSM's NVM is what we're exposing. The key manager does support local NRAM keys for less secure items, but likewise has access to the HSM keys as needed to be used. Those keys that can't be exported, like private keys of a PKI set, obviously the client would not get access to, but you'd be able to use them in a proper sense. And likewise, local version of wolfCrypt, which may be configured completely different than the way the wolfCrypt is on the HSM, to ensure that, hey, maybe there's features that you need here that you don't need on the HSM. And then likewise, an offload to the HSM core. From this perspective, though, it's just going to be a library. We're expecting to be linked into the current application. Hopefully, we can control the memory space through tailoring, and then make sure that we don't have any ongoing tasks or things that are going to weigh down that application core that's not related specifically to communications requests and responses. So I think this is just more of what I just was talking about. Again, our target here was to build these as libraries for the client side that can be linked into existing code. I'm just going to click through a couple of these items. So notice we're plowing through time quickly, and I want to make sure we get to the demo and we can walk through these. So as an example, I'll walk through what this API looks like. This is on the server side. On the left would be an example of the code of us doing a standard AES initialization, setting a key to perform an encryption, performing, in this case, a CBC encryption, and then freeing that context after. So from a pure wolfCrypt perspective, this is where you know the entire key yourself, and you've got it locally, and it's just encrypting, in this case, some data, some plain text data that ends up into ciphertext. The switch for this, when we're using a key ID instead of the actual key material, is we would reference which HSM key we need to use. This is in case this is a hardware key, identifier number, again, placed in there at some point. Maybe it's a static key, maybe it's something that we had loaded from NVM. We do the exact same initialization, except this time we point it to use the hardware crypto engine as for this AES call. We then update this using the key manager interface to say, hey, for this context, now use this new key ID that only the HSM knows about. Same exact everything else, perform the encryption, and boom, we're free. And so you can see a very similar flow in terms of what the code looks like from a pure software perspective, where you know the key material, to simply a key ID and moving on. And this was exactly the intent, was to not break the API significantly. Same type of idea here, but now this time we're going to go ahead and provide that we've got a user key that we want to load into the HSM, and then use that. HSM can then use that key. So probably not a decent security solution, but this would line up with something. Let's say you're performing some CAN bus operations and you needed to establish a session token. Session token's computed, you extract a key material from that, send it to the HSM because it's got offloaded AES. And from that point forward, you'll get HSM accelerated encryption. And it's the same sequence where we are passing in. This time we don't know what key ID we want to use. We're going to let the HSM pick that for us. We import the key from the key contents into, and it will tell us what key ID it's going to be using because we started off with an invalid key. We then say, hey, for this context, use that key ID that we just got back, perform the encryption for us. And again, this encrypt is really just a message from the client to the server saying, hey, HSM, do this encryption for me. HSM finishes it off, provides the data back, and we're off to the races. And from a code perspective, it's identical code for the actual encryption. The last piece we did here was just showing that, hey, because we allocated a dynamic key on the server, we probably got to free it when we're done with it. But that's really the essence of the changes in the API. So again, not a significant change to the APIs from a wolfCrypt perspective, but it's matching this mindset of being able to offload operations to the hardware when necessary. NVMs, on the other hand, lots of different ways of doing non-volatile memory. None of them are good for fail-safe operations. And so one of the critical aspects we see is that being able to detect and then recover from a broken or a failed flash write is very important. And from our Wolf boot days, we've spent many years working on how to always ensure that we can detect the corruption and then correct from that. So what we found in many of the HSM solutions that are out there, the erase sections for flashes are huge, like a significant portion, sometimes half of what's allowed to be done. And so what we wanted to make sure was that you can't just, write something and erase it and then write it again. It's no, you write something, if you don't like it, you have to erase the entire chunk. And very often you don't have enough RAM to even remember the stuff that's there. So you're going to have to use some smarts on how you manage that. So the NVM manager handles this for us, provides a sequence of flags in a very strict sequence that allows us to detect exactly what was going on and whether it completed or not, sort of like an integrated transaction log, if you will. It lets us replay and recover the data as we go. Now, we don't need full-blown, completely arbitrary data that looks like files. We instead say, no, we really just need to have some way of associating some metadata, which would be like an ID, some sort of string label, maybe a path, if that makes sense for that, some length of data that's going there, and then to be able to associate that with a chunk of data that's in NVM. And that's all this NVM manager is trying to do. Given an ID or given a label, here's the chunk of data that goes with it. And we're not talking about huge amounts of space here. These are tens of kilobytes, if even. So we wanted to make sure this is tight and it doesn't get in the way of the limitations we've got on the flash. And so the solution here is that you create an object, or you would add an object, and it's going to find the next available space in flash. It'll put the data in there, update the flags, and if at any moment we've lost power or something fails, by reading through which flags have been set, flipped from erased to programmed, we can decide exactly how far along in the process we were when the operation failed, and then recover. When you wanted to remove something, you in essence say, these are the objects I no longer want. You would then copy everything from one partition to the backup partition, the things that you wanted to save, which would also defragment everything and bring things back into the way. That way you'd know it's exactly there. If that operation fails halfway through, it's okay. You'd boot back up, realize you don't have anything that has been completed. You would ignore that second partition and it'd be as if nothing had even happened. And that's really the mindset that we've got. Well, excuse me. From a layout perspective, we accomplish this by providing a fixed directory that has a certain number of entries in it, which is set at compile time. And then the rest of the space is used for appending the referenced data objects back to back into that stack, if you will. Always split at least the NVM sections into two equal parts. So we always have two partitions, an active and an inactive. And this allows us to, as you want to make changes, if you're not just full on appending, you need to remove something, or you need to reclaim the space, you'd have to copy everything to the second partition, verify it's good, then wipe out the first partition. And so you would then be able to use the second partition's copy of everything. Again, I won't walk through too many more of these details because I'd like to make sure we have plenty of time to walk through the demo. But this kind of walks through the complexity of how we had to handle doing this on Flash objects with different flags that are written in a very specific sequence so that we can always recover. And again, these slides will be available after this as well if you guys want to dig into any of that as we go. Let me finish off this NVM. So from a source code perspective, things in blue are kind of new. This is now written from the client perspective. So kind of showing the first set of examples was what we did directly on the server, which is a little more direct. On the client, everything is now proxied, if you will, through the communication layers. But in terms of an NVM solution, we light up this is the left-hand side's a writing solution. We're adding data in there. We identify the metadata we want to set. And again, the labels are large. They're 24 bytes in the current build. So you can actually sneak data in there if you needed to and not have any actual data. The labels are indexed. So you make sure there's nothing private in there. This is heads up because those are retrievable. And then likewise, you've got an ID value that lets you identify uniquely items that are in there. You'd invoke an add object, which simply says, using this metadata, put this data somewhere into the Flash, and then I'll be able to access it via that same metadata, either the ID or search for it by label. if I wanted to update that same data, again, it's an append type of solution. So if I've got the same exact ID value that I'm using, and I add that object again, the previous instance of that object will no longer be looked at. It'll be ignored. It'll be wasted space, but you'll be able to see the new version of that object the next time you boot, or in obviously during runtime. So because it's an append-only solution, until you have to remove something or reclaim data, we avoid a lot of erase cycles and simply keep stacking things on. Obviously, there's some statistics there to keep track of how much space you've got free and how much you could reclaim by regenerating the partition. But in terms of base mechanics, I've got metadata. I've got some binary data I want to place. I did strings, but it can be binary. It's not a problem. And updates are the exact same fashion. To read that stuff back, in this case, we identified just the ID value we wanted to find. Say, hey, go get me that metadata from that ID. It gives us the metadata, which now the metadata keeps track of how much data we actually wrote in there. And now I can go ahead and read the data back using that ID value that I've got. This is an offset, so this is from the beginning, but I want to grab the exact length that was written. So even though I have to write in fixed size chunks based on what the flash constraints are, I can pull that stuff back in bite-sized and go from there. So this is writing stuff, data and metadata. This is reading the metadata back and then reading the data back. So pretty straightforward API. It kind of matches the ability to do transaction-based NVM updates. We've got some abilities to list and search through objects that it can find. And likewise, the destroy objects is what you would invoke to get rid of existing objects or to force the system to force an entire copy of the partition to reclaim the space that was being wasted from overwritten objects or half-written objects as well. So currently, we are planning to port this solution and then provide support for the Infineon RX TC3 series. In fact, we'll be demoing today on a TC367 DP. And we'll kind of walk through how this is going to work. But on the books today is at least the TC3X and the SPC58 NN. This is the RX solution is tri-core application cores with a Cortex HSM and M3. Again, you can see the speed difference between these two. And again, you've got structural differences and DSP differences between the CPUs as well. On the ST part, the SPC58 series, it's got 3 PowerPC units, including floating point, including flash, including caches. HSM is running at half the speed. It doesn't have floating point, doesn't have cache. So you can see why the configuration ability of a wolf crypt on one core is fundamentally different than the way we configure it on a different type of core. The ST part, again, has a limited amount of hardware offload. It only does true random number generation and AES-128 in multiple modes. So anything that's outside of those two operations, any elliptic curve operations or RSA, has to be done specifically in software. The tri-core has support for EDCSA as well as 25519, and as well as for the SHA-2 or really SHA-1 as well engine. So it's got a few more items there to do that. But that's where we are currently on the books to support. But any ideas on any other targets, please feel free to talk to us, and we'll be happy to take a look at what it would take. So let's get to the demo portion of this. And again, we've got a dual core or 2 tri-core application cores. This is a TC367. It's just a standard dev kit. Nothing fancy about it. It has been enabled with an HSM core, and the core is now marked to always boot. It's still in the confirmed mode, so I haven't locked everything down yet, so it still allows us to do development. And again, we've set up crypto offload for a bunch of those algorithms we just mentioned. But let me walk through what you're going to see as we go over to the demo screens here. So the very first thing that happens is on this system, both the HSM core and core 0 on the tri-core are going to boot up. In this case, they are marked to be in parallel. The tri-core is then going to issue a request to the HSM to say basically hello, and the HSM responds back saying, hey, I'm here, I'm ready to receive requests from you. And so that's what we call our initialized communications sequence. And you'll see that happen very quickly, right at the beginning right after reset. Right after this, the TriCore is going to perform our standard wolfCrypt test application, and then followed by the wolfCrypt benchmark. And this is running completely on the TriCore by itself. The HSM is sitting simply idle, and it's performing our standard tests. And this is the same code we use whenever we port our products to a different core. We run these exact same tests. Any outputs that you see are going to be redirected through serial port, and we capture those as we go. After it's done, the TriCore has completed both its internal software wolfCrypt test and software wolfCrypt benchmarks, and provides those numbers. It then commands the HSM, which is an ARM chip, to perform wolfCrypt tests on its side and then feed the results back. It then commands it to do the benchmark and then feed the results back. After those, it then commands it to do a pure hardware true random number generation test, which is just a separate test that we've added that directly accesses the crypto hardware on the chip to just verify that the the random number generation is good. We use that to seed the TriCore's local pseudo random number generator, which is a typical sequence you'd have to get good random numbers at your TriCore. The HSM gives you a good random number or entropy to start off with. You use that to seed, and then you can generate local random numbers based on a deterministic random bit generator. After that, the TriCore is going to ask for a sequence of custom callbacks. This is that extensibility that I talked about that allows you to add additional code into the HSM to prove that we can do arbitrary things if you'd like to. And the last piece we do is we walk through and we command the HSM to do known answer tests on each of the low-level versions of those hardware crypto operations. So things like the elliptic curve functions, it's not like perform elliptic curve. It is perform all the intermediate point multiplications and additions. So this low-level hardware crypto test is going through and doing known answers on each of those things. And that's, I should also point that out, when we perform a wolfCrypt test, we're performing typically NIST-related test vectors to make sure that we're getting exactly the right answer. And if anything, any bit is wrong, we halt the test immediately. All right, so from the TriCore's perspective, in this case, again, we've only got 2 cores. We have only enabled an HSM client on core 0. Core 1 is simply spinning. It's doing nothing, not getting in our way. And we're running a standard boot and listening for requests to come in here. So this is kind of how that diagram lines up in real life to what we've got going on there. All right, let's switch over. Some other points I wanted to make. The TriCore app we built using, let me go back. Built using the RX Dev Studio. Using the GCC compiler engines, we configured wolfCrypt to enable single precision floating point optimized math for the TriCore. We don't have customized assembly for that platform yet, but the floating point does a great job on this engine. And so it allows us to configure wolfCrypt specific to that core. The HSM app we built using a standard GCC-based ARM toolchain. In this case, we did enable, we have customized Cortex-M assembly code that we enabled for this Cortex-M3 that is on the HSM. But again, from a build perspective, completely off the shelf ARM toolchain as a Cortex-M3. All right, so let me switch over and get to a remote session here. All right, so I'm gonna hit the reset button. So this is I apologize. Let me reset this scroll back here and clear it out. All right, so I'm gonna hit the reset button, and this is gonna go pretty quick, but I'll scroll it back up. So I just hit the reset button on the dev kit. I'm gonna scroll back up so we can watch what actually happened. And here we are. So this TriCore initialize, that's the very first thing that comes out of the serial port that the TriCore is through its actual startup sequence, and then it was able to reach out and talk to the HSM. This HSM initialize doesn't return until after the HSM has responded. So the HSM did respond. We jumped directly into the wolfCrypt tests, which is, again, local software on the TriCore. Note that we're running wolfSSL version 5.5.0 on the TriCore set. And what this does is it goes through our standard wolfCrypt test, verifying local functionality of whatever features were enabled on this TriCore. So in this case, we enabled SHAs and HMAX SHAs, the TLS 13 KDF, GMAC computation cha-cha, but these are all known answer tests running in software on the tri-core 300 megahertz. After it completes that, the return code was 0 that says, hey, there were no faults. Every known answer test came back, and we were good to see that. The next is the benchmarks, again, running locally on the tri-core, producing results here to the serial port. So we're seeing generating random number generation at reasonable rates for a 300 megahertz microcontroller, running through different AES sizes and lengths, and a couple different GCM versus CBC. And so we're seeing some performance there, which is good. The GMAC we're using is a table lookup using 4 bits, and it gets reasonable performance for that as well. These numbers, by the way, you'll see a copy of these also in the slide deck. Some additional cha-cha and poly algorithms. We're seeing RSA operations, public operations, and private. Again, all local software as it's completing off its run. At the end of this benchmark test, it says, hey, every benchmark we ran successfully, and you're seeing some performance numbers that are reasonable. I'm just going to pick out a couple just so that we've got some points to reference. Let's take a look at AES 128 CBC. This is the encrypt side. So the tri-core running at 300 megahertz gets about 3.7 megabytes per second in software. So just remember that number and we'll be able to continue on. After this, the tri-core then commands the HSM to perform its series of wolfcrypt tests. And again, all we've done on the HSM side is taken the same exact test code and then redirected the printf outputs through a shared buffer that goes back to the tri-core, and then the tri-core sends it out the serial port. So this allows us to see output in, again, a debug sense of what the HSM is performing. We're actually running a different version just to prove that we can do it of wolfcrypt on the Cortex-M. And again, it's been compiled with optimized assembly as opposed to being in tri-core. Again, it runs through all the tests for everything, all the features that were built in. And you'll see in this case, you don't see cha-cha. You don't see some of the other algorithms, again, configured, tailored down to be just what we should have in the HSM core. After it completes that, the tri-core again commands it to run benchmarks. And so these are wolfcrypt software-based benchmarks on 100 megahertz Cortex M3. And again, we'll just pick on this number right here. This is the AES CBC 128 encryption. We're going to get about 288 kilobytes per second. Again, you can do some math and say that's probably reasonable for that clock speed and the limitations the way that processor runs. And again, these are in 1K blocks, so it's not giant, huge streaming amounts of data. We plow through some different pieces. Get to the bottom of this. You see RSA operations. You'll see ECC operations. Again, all performed in software at this point, just to prove that we can fill in the blanks even when the hardware can't do it. Test is complete, no problems. The next step was the tri-core commands a pure true random number generation. It's a single call, reseed your true number generation and give it back. We then use that value to seed our local random number generator. And obviously we're just getting a random number, which sounds good. The next step is we command the HSM through a custom callback. Hey, make me an ECC key pair. And so we command it, the HSM computes it locally in software, sends the result back, again, proving the ability to add custom callbacks. The next one was doing a custom write to HSM memory. This is bypassing our NVM solution, just proving that we can do this if we needed to. It allows us to write a specific key out to flash and then verify it was written correctly. And then after this, we go through and we verify all of the low-level hardware crypto that the Infineon part can perform. Again, just as a point of reference, we're asking this AES CBC encrypt engine. This is a slightly different setup, so the performance is going to be different type of setup. This is assuming that you're doing a whole bunch of small messages. This is a 256 byte message done 4,000 times to get to a grand total of 1 megabyte. This is a lot different than, say, doing an AES CMAC on a huge swath of data that would perform potentially higher. But from the HSM's perspective, you got about 3.5 megabytes per second of performance with the hardware offload. Again, remember that was like 300 kilobytes per second if we did it in software. So definitely hardware is there and available. And again, this is not set up to do streaming optimization. It was strictly for a quick number. You can get much higher performance if you need to tune it for a streaming operation. But we do perform a sequence of known answer tests, and you'll see all the internals of some of the PKI operations going through there. And these function names, these are Infineon provided functions that we're invoking and testing those operations for. All right, well, that was the demo portion. I'll try to switch back so we can get as quickly as possible to some of your questions, and then make sure that I can get some of those answered as quickly as possible. This was, again, just a printout of the same thing you just saw, but obviously that was done live. All right, future directions. We are looking at the TC4 from Infineon as a potential port, the Renesas RH850 series. We think that's going to be a decent port to put this on. Don't have it directly on there. And the last one was a TPM backend, which is in essence running the HSM server code locally, but only using a TPM as an offload in case you don't have a chip that has an actual HSM built into it, but you still want to use the same mechanics. So we believe we can be able to pull that off as an additional port potentially in the future. Some additional protocols to consider. Providing us up as a full-blown PKCS11 would be one. Providing an elliptic curve-based bus encryption solution to go between client and servers when they're not tightly bound inside a shared memory area, or that shared memory transport can't be adequately protected. And then lastly, taking a look at what AUTOSAR and SHE, or SHE Plus, as some people say, what other parts of those might we want to teach the HSM to respond to as well. Obviously, in the future, access controls would be something we think would be a good addition. If you can't control your application space, you definitely want the access controls to ensure that even internally, a bad actor on one of the cores couldn't violate something else if that trust is broken. And then likewise, supporting multiple sessions. So if you do have VMs running on a client, that you can keep those different instances straight, even if you've got them coming from the same effective port. So, all right, well, let's that's what I've got to talk to you about today. Let's see if we can switch into some of the questions. Let me just go through what I'm. Go ahead, Shizuka.
So there's a question. If you implement Auth Manager, wouldn't you identify how to be from a trusted server? Normally, you would present a digital signature to the HSM, and then thus you obviously should not store the private key in the app, a pass-through authentication from a server.
Yeah, that's a great question. This is also why Auth Manager is not implemented in PSA. It's a hard question to answer. But yes, you would want to ensure that both the client and the server have some way of authenticating each other. We would probably take a look at stealing some pages from TLS to ensure that both sides have a common root certificate, or can otherwise verify that their identity is who they say they are. Absolutely leverage asymmetric cryptography there. In tightly coupled situations, you can measure the code they're running and potentially challenge that. And there's ways of doing attestation that could prove that code base has to be who they say they are. And that may be an alternate method of don't believe me who I am. You can measure me. You know who I am based on my measurement. Again, those are features that could be taken a look at if you needed to change the security profile. Hopefully that answered the question.
There's another question. Can our application simply use an OpenSSL 3 provider, then have the wolfHSM, wolfCrypt, etc. hidden behind the provider so that we do not need to deal with them?
If you're asking if your application could use OpenSSL and then use Wolf Engine as the provider, and then that engine could reach out to an HSM, I don't see any reason why that wouldn't be possible. The idea here was to be able to expand the usages of that HSM. If we're simply using wolfHSM as a transport for communications that came from, let's say, an OpenSSL front end, I think that's entirely possible to do that, and probably a valid use case for us to take a look at.
Another question, when would the HSM code be available to evaluate for an OREX TC387?
We're on tap to have our TriCore, or a beta build of our TriCore, which means feature complete, by the end of this year. There's a couple of hurdles to overcome with that. I mentioned NDAs, so we'll definitely want to coordinate to make sure that you're able to see that code, and that any of the vendor code that we had is properly protected. But I would ballpark an engineer saying a time and money is probably not a good idea. But we're on schedule for by the end of the year to have that demo and that stuff being able to be pushed up and then shared.
Another question, how do you guarantee intercore isolation?
Fabulous question. That's definitely target specific. I'll pick on the ST part as an example. The ST part has multiple cores, and for each core, there's a crossbar that has a memory protection unit that you can specify how memory transactions can go across that crossbar. Those MPUs can be configured by the HSM specifically, and then locked down so that no one else can reconfigure the MPU. For the communications buffers, we allocate separate buffers that are on page-based granularity, and set the MPUs up to ensure that only those pages in memory in the shared global address space can be accessed by that specific core. So to answer the question, how do we guarantee intercore isolation for communication buffers? We specifically rely on the vendor provided memory protection units, or whatever other mechanisms they have, to ensure that address accesses to specific shared sections is guaranteed. There's nothing else that we add on top of that, but we've had to, at least for the two that we're currently working, which is the ST part and the TriCore. Hopefully that answered that question. If there was a more fine-grained level of control, this is where we think the access controls, that addition that we could do in software, might be necessary to pull that off. But also, I was going to say, pointer address validations for DMA operations, you can't say encrypt this chunk of data and write it to this guy's core memory. We detect that instantly and deny that as a bad argument. So we do understand where those requests are coming from.
And another question, is the code from your demo available for us to look at and experiment with?
Not quite yet, but again, if you take a look, if you can wait till the end of December, we'll have that stuff pushed up. And again, some of that code will have to be handled to be compliant with the RX and the Infineon NDAs. So once you get an NDA with Infineon, this is stuff that we could then work on getting shared out. Currently, we're developing this in a private repo, but once it's done, we'll open that up and make it, as much of it as possible, public.
Another question, would the potential update of a wolfHSM be handled by wolfHSM itself, or is a separate update manager running on the HSM required for?
That's a great question. If you consider the sequence that we use to boot the HSM from an initial bootloader to an image manager to an HSM server, you can almost imagine those are three separable modules, whereas that initial boot would likely be immutable and would have the ability to handle self-updates. So we have not worked that solution entirely, but it is highly likely that we would want the ability to perform a partial self-update of wolfHSM to handle any significant issues after it's been deployed. There's a number of provisioning steps that have to go through to ensure that we can authenticate the incoming update and verify that it's intact and can be written there. Some of the code space inside of some of these HSMs is already split off to kind of support a small bootloader and then two potential options for loading. Again, all of that is in the realm of possibility. I think it's going to be highly target specific to do that. But self-update is something we've supported in Wolfboot for years now. And it's hard to get right. I can tell you that. But it does tend to rely on a provisioning sequence that allows you to place a little piece in there initially and never touch it, and then be able to update the rest of the sections as you go. Yes, potentially technically feasible. it's challenging, and we've thought about it ahead of time. So hopefully, as the time comes, we can get that feature put in and really make it something that would be a differentiator.
Another question, can you provide a library to utilize Ulrich's hardware accelerator for ECC?
Yes. So the way the crypto callbacks work for us, that would be exactly what you would end up with, is that you would get your ECC operations. It supports up to ECC 256. And many of those operations can be hardware enhanced. The way we code up our ECC, we can also break off individual point operations to be hardware offloaded, and the entire sequence, but though, could be controlled or filled in with software. So can we provide a hardware? Unfortunately, that only is accessible from the HSM. So you'd have to provide not only a library in the HSM, but a server to listen to the request to execute. You can't access the cryptography backend except from the HSM core.
Another question, how do you integrate into AutoSAR?
So from AutoSAR, the expectation is that we would be beneath a crypto, let me see if I get this right, crypto provider. And they've got a couple different layers, not a crypto manager, crypto provider. So the expectation is that we would provide interfaces up that you could implement into a crypto provider that would handle these pieces down. We don't intend to reinvent AutoSAR or to directly supply a crypto provider library, but we think we can give enough of a sequence that lines up with the AutoSAR mindset that it would be pretty straightforward to provide that wrapper library. So how do I integrate? We haven't done anything that violates AutoSAR from a logical perspective, but that may be another opportunity for an alternate protocol to talk to us.
And another question, are you certified to Automotive SPICE?
That's a great question. So this code that we're cranking out now, we don't have a requirement to be certified to that, but this may be something that would be required for us to be able to provide to the automotive market. Again, our goal is usually to deliver source code. And so what we deliver to our customers then go get those things certified. So we do like to make sure our code can pass muster with all those types of analyses and structures that would require us, and processes really, to be compliant with a SPICE or a MISRA, but not necessarily get our certifications ourselves. So to answer your question, are we certified? No. Could we be certified? Very likely. Would we help our customers get SPICE certified? Absolutely.
Another question, what do you do to meet startup time requirements about 250 ms with secure boot?
So that's a great question. One of the biggest things we found is that you will not win if you have to do all software based measurements. So the key here is to be able to offload to the hardware engines as much as you possibly can, and let them plow through the huge chunks of data. And so what we're finding is that a reasonable chunk of flash on some of these boards, if just the raw crypto engine with no software running, you're in the 30 to 40 millisecond range already. And so the ability for us to boot up quickly with a tiny bootstrap, set up the environment we need to execute, trigger the engine to work, to start to measure in parallel to us completing the rest of our setup of handling, communications and stuff. That's definitely a challenge. But again, it comes right back to the exact configuration that you allow your system to be in. So one of the easy solutions is to that's a very good point. It's huge. Yeah, you can't measure the whole shebang. In my opinion, I don't see a way to do that. But to break that off, and then to allow you to start those cores in parallel. So let's assume I let the application cores boot, assuming the image is going to be good. The HSM starts to measure that. And then after, say 200 milliseconds, we realize, oh no, this is a bad idea. He's running the wrong load. the HSM has the ability to drive those guys back into reset and then set a fail-safe condition. So if instead of having to wait for the entire time, the 250 milliseconds or however long it takes to really measure that, and then start the application cores, there's an opportunity here, and this is typically allowed even in SHE based solutions to kind of pull the plug after it's been started. Again, it definitely relies on the target and the hardware being enabled, but parallel boot is definitely one way of attacking that. Heavily leverage the crypto hardware offload and the ability for the software core to continue doing other work while the hardware is chewing on all of that data. One of the things I was going to mention on that is that performing measurements on software updates may not meet your 250 millisecond time. So I may want to, let's say someone sends me an update for an application. That application, for me to measure that with, let's say, an RSA or something or other, maybe it may take me 10 seconds to solve that, to see, just based on the math involved. But then once I've applied it and put it into the hardware, I may switch the authentication method to something like an AES CMAC, which would be hardware offload enabled. And so the critical runtime startup sequence might use a different authentication method that I've computed on the fly during the software update protocol than what I would have done to accept a software update. Because it's not like they say, you got your software update, you got 250 milliseconds to verify. I may have a lot more time during software update to do that. So switching that verification method, maybe a third strategy to help maintain your startup sequence timeline.
Another question, do you meet ISO 21434 in development?
So our development processes, we've got published on our website. They don't violate 21434. That is more of a guideline, if you will, to follow through. What you'd really want to be certified against would be a 636. So we don't necessarily aren't certified to do that, but our processes line up very well with 21434, and we would be able to produce many of the artifacts you would want to see to verify your safety critical verification. But from a cybersecurity perspective, there's nothing we do that's outside of what will be called out there, but we don't necessarily follow 21434 letter of the law. But again, it's things we do the right thing. And our software development process, if you line that up with what 21434 calls out, you'll see, hey, there's a lot of overlap, and a little bit of analysis, you'd be able to show coverage for all those features.
Okay, thank you so much, Bill. Yes, go ahead.
I was going to say, you answered my own question the same way. So thank you, Klaus. That's an excellent point. Thank you very much.
Hey, Bill, I answered some questions in text during the seminar. I didn't understand the flow. Did you want to go over those again?
Doesn't matter to me, whatever you like to do. Is there anything in there was there any questions in there that I didn't hit?
We got one. I used to think that HSM is a hardware device, and is wolfSSL planning to manufacture a hardware HSM?
Oh, that's a great question. Not as far as I know. Our goal is to be staying in the software realm. Now, whether our software might be embedded in someone else's HSM is a different story. But no, I don't think we're going to get into the hardware world anytime soon.
Okay, and then what do you call hardware crypto? Does firmware implementation count, or ASIC only?
No, firmware would be 100. In my opinion, firmware is on the hardware side. The question is really, is it a general purpose CPU core executing it, or if I've got gates or ASICs doing it? To me, that's hardware.
Okay, and then another good one. Usually ECU and HSM are not programmable to reduce the exposed attack surface. Why are you diverging from this approach?
Specifically because the welding the hood shut is probably not a good idea based on the uncertainties in cyber. Watching different algorithms come and go, watching different attacks that you thought you'd mitigated against all of a sudden come back and bite you. Not having the ability to update all of those is probably not the best path forward. If you don't want to support in-system update, perfect. We have no problem with that. Turn all those features off. If you do need to support it, and I think it's probably something you should be considered, definitely it's nice to have it built into the design so you can support that down the road.
Okay, yeah, my answers were pretty close. That's it.
Okay. Thanks, John. I appreciate
Okay,
that.
perfect. Perfect. Thank you so much, Bill, for hosting the informative webinar and everyone for joining the webinar today. Please don't forget to follow us on Twitter at wolfSSL as well as at the social. Also, if you have additional questions, please email us at fax@wolfssl.com. And thank you again and see you next week.
Thanks so much.